Okay, one more example. This time I'm just going to run straight through the drill here of using our rules from the last example. In order to find the zeros of this polynomial, p of x equals 2x to the fourth minus 5x cubed plus 3x squared plus 7x plus 3. And what I always start with is finding my y-intercept. And in this case, p of 0 is easy to find. We know that p of 0 is equal to positive 3. And I also know that by my leading coefficients test, it's a positive leading coefficient with a even degree, so the graph will be going up on both sides like this. All right. Now, we use Descartes' rule of signs to count the number of possible real zeros on the left and the right. So if we look at p of x, the natural function, we see that we have one sign change, two sign changes. So what Descartes would tell us here, I can spell his name, that's the problem with French, Descartes. If I checked out his rule, he would say, well, p of positive x tells us that we are going to have two or no, zero positive real zeros. And then we would check out p of negative x. Well, p of negative x is going to change the signs of our terms, at least some of them. For p of negative x, we would discover that we're going to have a positive first term. 2 times negative x to the fourth gives me positive 2x to the fourth. We would end up with a positive second term. Positive 5 times negative 5 times negative x cubed is the same thing as plus 5x cubed. We'll end up with a negative next term, negative 3x squared. A negative 7 times negative x is positive 7 on negative x, it's negative, plus 3. So we have, again, one sign change, two sign changes, so it implies that we would have two or possibly zero negative real zeros. Okay, then we're going to use our rational zeros test and look for the list of possible rational zeros for p over q, which are factors of our constant term over factors of our leading coefficient. Well, factors of our constant term include plus or minus 1, of course, plus or minus 1/2 when we take 1 divided by 2, plus or minus 3 over 1, or plus or minus 3/2. Thankfully, this is a very short little list for us to have to check out. So what we're going to do is we're going to test our zeros by using synthetic division. And so I'll start on the positive side this time. Let's say I guess that x equals positive 1. I've got a 50-50 chance of this working. Let's see. If I put in x equals 1, what happens? Well, if I check out x equals 1 in synthetic division, I've got 2, negative 5, negative 3, positive 7, and positive 3 is my coefficients. Carry down the 2, multiply by 1. Negative 5 and 2 is negative 3. Multiply by 1 to give me negative 3. Add down the column to give me negative 6. Multiply to give me negative 6. Add, we get positive 1. Positive 1 times 1, that's 1. Add down the column, that's 4. Well, that's not much help, except I don't want to lose track of this because we know by the remainder theorem that we now know that p of 1 is equal to positive 4. Let's try the next positive whole number here. Let's see what happens at x equals 3. Anything good? Well, I know that at x equals 3, if I were to put in synthetic division, 2, negative 5, negative 3, positive 7, positive 3. Look at my synthetic division remainder. 2, this is 6, this is 1, this is 3, this is 0, 0, 7, 7 times 3 is 21, 21 and 3 is 24. That's not very helpful right here. Well, let's see. So, but we do know that P of 3 is equal to 24. So it doesn't appear like we're getting many results on the positive side. Let's go to the negative side at x equals -1. I would just go through and list my whole numbers, right, one by one, and just see what happens. Right, so let's see, at -1, I'm going to get, let's see, here's 2, here's -5, here's -3, here's 7, here's 3, 2, carry down the 2, that's -2 now, so I get -7 right here. Now I get -1 times -7, that's +7. Add down the column to give me +4. -1 times -4 is -4. Add down the column, that's +3. -1 times -3 is -3. Hey, we've got a 0. That's actually really, really helpful. So now we know that one of our zeros is -1. P of -1 is equal to 0. And what's more, we also know that we have a reduced polynomial right here of 2x cubed minus 7x squared plus 4 plus 3, 4x plus 3, pardon me. Right. So now we would want to think, well, what any other zeros that we have are going to be zeros of this thing. Well, what haven't we checked? Well, we could go to our fractions. We go out to -3 and see what happens right there. I don't know if that's going to help us much, but we could try x equals -3. I'm going to go over here. I'm going to just try some of my positive fractions. Let's see what happens at 1/2. Will that work? I'm going to use my coefficients for my reduced polynomial. Let's see, 1/2. Does that work? Remember, I'm going through my list of rational zeros, so now I'm going to use my reduced polynomial to help me find my remaining zeros. So I've got 2, -7, +4, and +3. Let's see, if I bring down the 2, multiply by 1/2, that gives me 1. Add going down the column, that gives me -6. -6 times 1/2, that gives me -3. Add down the column, that gives me 1. 1 times 1/2 is 1/2. Oh. Well, not much help, but let's see, 3 plus 1/2, that's 6/2. That's 7/2 right here. We know that at least x equals 1/2. It's not a 0. Let's try our other positive fraction, 3/2. We might as well exhaust the list if we've got it. And next I'll go to the negative fractions if we need to. But let's see what happens here. I've got 2, -7, 4, and 3. So I carry down the 2 right here, multiply it by 3/2, that's 3. Add down the column, so that gives me -4. -4 times 3/2, well, remember, you divide 4 by 2, that's 2. Times 3, that's 6. So -6 goes here. 4 and -6 gives me -2. -2 times 3/2, that's the 2's divide out, giving me -3. And whoa, hey, we've got another 0. That's excellent. We now know that x equals 3/2 is another one of our zeros. And remember, Descartes' rule of sign said that either we're going to get 2 or 0 positive or negative real zeros, so there has to be another positive real zero. But what's up with this? Look, we've covered all of our positive numbers, 1, 3, 1/2, and 3/2, and only found one real zero. What gives, Professor Peoples? Well, don't forget about this reduced polynomial, which is now 2x squared minus 4x minus 2. If there are any further zeros remaining, they will be zeros of that polynomial. So once we're down to a square, we're home free, right? Because that means that any other zeros we want to find are going to be zeros of that polynomial, of that reduced polynomial. So we set it equal to 0, and let's see what we can find. Well, everything's divisible by 2 right here, so I'm going to divide both sides by 2 to give me x squared minus 2x minus 1 is equal to 0. I'm going to move my constant over, so I'll get x squared minus 2x equals positive 1. Yes, I'm completing the square. I take 1/2 of negative 2 squared and add that to both sides, so x squared minus 2x plus 1 is equal to 2. And on the left-hand side, this factors as x minus 1 quantity squared equals 2. Therefore, x minus 1 is equal to plus or minus the square root of 2, which is to say that our two zeros are going to be 1 plus the square root of 2, and x equals 1 minus the square root of 2. So you look back at this list right here, say, well, okay, our zeros then are x equals 1 plus square root of 2, x equals 1 minus square root of 2, x equals 3/2, and x equals negative 1. Does this fit those conditions? Well, sure. We have two positive real numbers. We've got 3/2 and positive 1 plus square root of 2. Those are both positive zeros, right? 1 plus square root of 2 is about 1.4. And we've got two negative numbers because 1 minus the square root of 2 would be negative, and so would negative 1. And not only that, we've got our rational zeros of 3/2 and negative 1, which were both on this list, but it didn't say anything about irrational zeros, and we can get irrational zeros, so it does fit the conditions of our rational zeros test, which only identifies possible rational zeros, not irrational ones. This is our list. We found our zeros, and so we're done. Good luck on the homework, and I'll see you in class.